Okay. Well, hello everyone. My name is Aaron Day. I'm a soil scientist at North Dakota State University. I am their soil physicist, which is a fancy way of saying that I study how things move, whether that be water, heat, nutrients, or the soil itself. But today, what I thought would be useful to talk about is a topic that we've hit at numerous events throughout the winter this year, particularly talking about and anticipating challenges with residue management, soil tillage, and with ruts, particularly in the context of following a wet harvest, like what we endured during the fall of 2019. And for potentially a number of folks who are still trying to get 2019's crop out of the field. So this video right here is going to be on that topic. And because everyone has their own unique situation that they are, that you're dealing with on your farm or on your clients' farms, I want to hit a few different scenarios. One of the scenarios is perhaps everything got harvested and completed, all your fall activities just fine. So going into the spring, it's going to be fairly business as usual for you. So we're just going to check mark that and say those folks are good, or at least know what to anticipate this coming year. Perhaps you'll get some interesting or useful tidbits from this talk right here. But if you fall into this category, or if some of your fields fall in this category, then we're going to consider those fields as good for right now, at least, and focus on some other situations that are perhaps quite prevalent throughout the region this particular spring because of our wet fall that we had. So the few scenarios that we will focus on a lot here is you got harvested during the fall and you're able to do it with no ruts, but you didn't get any of your fall preparations done, any of your fall field activities after that harvest was there. So got in before the wet conditions, or even after the ground had frozen, but perhaps you're dealing with, especially if you're used to tillage, you're dealing with going into the spring with much higher residue levels than perhaps you're used to in the past for it. So how to manage that. Perhaps you're still waiting to harvest. That 2019 crop's still in the field, so time will tell depending on what our spring holds for us. I know that even folks who were harvesting in the winter, by time February hit, there was people that were finding thawed soil out in their field and were sinking in, having quite a difficult time getting in a harvest because we didn't have much of a frost depth this year. The early and continuous snow cover that we received, most of the soils here, at least in the valley and extending outwards from the valley, maybe only froze a foot or a little bit more, and that was it. And so by time February came around, the soils had to actually fall from the bottom from deeper heat, thinning the frost layer, and you had snow-covered soils and fields that had no ice in them though. So that's a troubling item if you try to harvest during the winter, but actually for the spring, it's actually kind of good because you get some faster infiltration and drainage occurring when snow melt has been occurring in these last couple of weeks here. So we'll talk about, for the folks that are perhaps still waiting to harvest and still have crops out in their fields. And then on the fourth item down here, we'll also talk about harvested, perhaps you got harvested in the fall or winter, but oh, look at those ruts. And the thing is, everyone faces tough choices, especially in falls like what we just had. And so some pretty substantial ruts, and ruts all across the fields were prevalent throughout the region, and was just a reality for a lot of folks on it. So we'll talk about dealing with those ruts and what you can expect in the years coming afterwards too, from compaction that occurred with those ruts in those areas. But items 2 and 3 right here, these different scenarios, just bear in mind that there's a lot of recommendations depending on when harvest comes, but the recommendations will kind of look similar because it's just a matter of when harvest had occurred at. You're going to be dealing with high residue situations in both scenario 2 and 3 here. So let's go ahead and get into that first scenario that we're going to talk about. So harvested in the fall, no ruts, but you also had no fall prep. So a lot of residue on the ground. Perhaps for the folks that are not accustomed to a no-till situation or a high residue situation for it. If you are a long-term no-tiller, then perhaps this is also just another, this is probably just business as usual for you. So one of the things that I like to point out, and I like this graph right here that I want to spend at least a moment going through, is when you have a lot of residue on the soil, the first things I start thinking about with spring planting is our soils up here being able to dry out so we can get in and get a good crop stand established and going. And so the water that's in the ground, it has 2 different routes that it can go. It can go up or it can go down. And the most efficient way is for it to go down. When you have a lot of residue on the soil surface, it limits the amount of evaporation that can occur. So you're reducing the amount that it can be lost upwards to let that soil dry out. So this graph right here, what it shows is that on the side here, it has the evaporation rates all the way from 0 going up to 1. So this would be 100% evaporation rate at the very top here. And we're looking at days on the bottom here. This is days after some wetting events. So this would be after a big rainfall event or the snow melt itself, something that would saturate the soil quite substantially. And then I've got a few curves on here. The very top curve, this one that goes just straight across the top, this is the atmospheric demand. It just sits at 100%. So if the air could have its way, it's going to pull every bit of water out. This is what it would be at. It would be at 100%. It would, the atmosphere would take as much as it can. The 2 other lines I have on here, the first one is a bare soil. That's the dotted line. That's pretty steep here after in the first couple days after a wetting event. So that's 100% bare soil, just completely bare. The other line, the solid one, is a 100% residue covered soil. So these are your 2 bookends. In your fields, you probably fall somewhere in between these 2. So I'm a big fan of bookends. What's the 2 ends? Because if you know what those are, then you have an idea of where you and everyone else are falling at in between. So the things on this graph right here to notice is that, of course, this bare soil, it's evaporating a lot more water than the 100% residue cover soil, as you would expect. This is very common and goes along with our intuition and experiences for things. But I want you to notice is that after the first several days, this starts dropping down quite quickly because the soil's drying in that terms, and a drier soil would evaporate not as fast as a wet soil. So it drops down quite quick over time. After about 3-4 days, it's actually over about 50% efficiency at losing water out for it, but it's still substantially higher than that of the residue covered soil. The residue covered soil right off the bat, it's losing evaporation at only half the rate of a bare soil would be. After 3-4 days. That now narrows up to where only it's about a quarter difference. And then if you look out here around 1 week and a little bit further, so in between like 7 and 9 days, the 100% bare and 100% residue covered soils actually come together. They converge together and they behave very similarly afterwards from there. So the point that I want to emphasize here is that yes, bare soils will evaporate more water than a residue covered soil. However, after about a week and a half, that's not the case anymore. It doesn't matter how much residue you have out on the ground. If it's been dry, everything's going to eventually look the same after about a week and a half. Now, when things don't look the same is if you get repeated rainfall events. So if we, as we continue into our spring here, which is when I'm making this recording here, it's mid-April. So if we continue this spring and we stay relatively dry, it's not going to matter if you have a lot of residue out on the field. It's going to dry out just the same as if it was a bare soil. But if we get in a situation where we get heavy rainfalls once a week, particularly twice a week, then we're really going to start seeing the issues of high residue cover be more of a issue with being able to get it in plant with it, because those soils are going to be wetter. So it really depends on what our rainfall is going to do for it. One of the things to think about too with evaporation and losing water upwards, drying the soil out upwards wise, is if you look at evaporation rates again here on the side where we're 0 up to 100% or 1 for the relative terms. And then instead of time after a wetting event, now we're looking at just tons of residue per acre. When we think of tons per acre, out on the field, we see a similar trend to where the higher amounts of tonnage, the more coverage there is, and the lower the evaporation rate. But the annoying thing is that different residue types will have their own curves, and it becomes residue type specific on what you can expect to happen. And that's actually an annoyance there. A much better metric to use for evaporation rates is actually not the tonnage or the percent coverage of residue. Those metrics are fantastic for indicators of things like wind and water erosion, but they're not a good indicator or the most precise indicator of how much evaporation you're going to lose. The better metric is actually the thickness of the residue type. And the reason being is that it almost doesn't matter at all what type of residue you have out there, whether it's soybean, cotton, wheat, or any other crop. They all tend to follow pretty much the same line. That's a very nice convenience for it. And you can see that in this graph right here. This is the same data set. It's just now looking at residue thickness in inches from the ground. So this is residue that's actually sitting on the ground. This is not standing stocks. So this is residue on the ground for it. And something I'll just point out here is that I put in a red line down here at the 1 inch thickness. And if you follow that up to the data and then go to the side, you'll see that at a 1 inch thickness, we're now down to about 30% of the maximum evaporation rate that is possible, that the atmosphere is thirsty for. So 70% of the evaporation rate drop occurs in the first inch. After that first inch, you go out to 2 inches, 3 inches, 4 inches. It matters a teeny tiny bit, very little bit. Most of the bang for the buck is in that top inch or in that first inch. So if you're doing some kind of residue management practice and you're thinning down 4 inches down to 2 inches, you're not really gaining much ground. It's not until you get underneath the 1 inch thickness that you see a big jump in the change of evaporation rates for it. But thinning down the residue layer can substantially change the evaporation rate. You can have very high coverage of the soil covered by crop residue and still being able to get it to dry out if you can thin down that residue management layer. And we'll show some examples of that in some trials and upcoming slides here soon. So in this graph right here, what I want to show is really a demonstration of that first graph, where we saw that a bare soil versus a 100% covered soil, after about a week, they started behaving the same on how dry that soil was if you didn't get an additional rainfall. So right here, that graph right there was a conceptual, what we see in many, many studies. A local example is on this graph right here. What I have is on the top graph, this is the soil moisture content in the early months a few years ago on a silty clay soil. So this is one of our Fargo soil series of very high clay and silt content for it. And this is soil moisture at a 2-inch depth. The bottom graph is the soil temperature in degrees Fahrenheit, also at a 2-inch depth. And we've got 4 different tillage practices that we had on this field. But the main thing I want you to notice is that you can see in this bottom graph, in the first couple weeks here, we had, temperature in the soil was right around freezing, a little bit below. So we're coming out of winter, and then suddenly you can see the temperatures jump up above 32, and we start thawing that soil. The first time that they jump above 32, if you look up here at the moisture graph now, you can see that suddenly all the moisture jump up real fast. That jumping of moisture isn't from snow melt infiltrating, it's actually from ice thawing. The type of sensors that we use are electric sensors, and any electric sensor, including the sensors that Indon run, has on their weather stations, and it's electric sensors is the most dominant type of technology that's used for soil moisture sensing. They don't detect ice, they only detect the liquid water. So when they're frozen and you see that, like, wow, it looks like the ground's really dry, it's not. It's just that most of the water is in ice, and it's more of an ice detector now. So, but that big jump, you can see that suddenly that soil thawed. And you can see, the types of tillages here, some had much higher water content, some had much lower water content when it first came out of the winter thaw. And they stayed different for about a week and a half. And then you can see they start coming together because we did not get another rainfall. And we actually had about 3 weeks without any rainfall event after the snow melt. And you can tell that first week and a half, there's moisture differences. The next 2 weeks afterwards, the soil is the same, dried out just the same. And to give you an idea of how much residue differences there were in between these tillage treatments here, some of these treatments had residue levels as low as 30% ground cover. Other ones had as high as 80% residue cover. So in between 30 and 80% of the ground covered with residue, they dried out the same and behaved the same because we didn't get any additional rainfall that occurred. It was a dry spring. So when it's dry, everything's dry. When it's wet, that's when you see differences in tillage and residue management emerge on the ability of the ground to dry out. So this is a local example. This was down around Moorton, North Dakota, on a Fargo silty clay soil. So early season differences in temperature and drying out after a wet spring or after a wet fall, or even in a wet spring, we think about that getting off the crop to a good start or a poor start perhaps. But does it matter by the end of the year when we look at yields? Because that's what we're really interested in, is how much we can sell our yields for to get an economic return off of them. So what I want to show now is some production scale tillage trials. That was a collaboration in between MDSU and University of Minnesota that included Jody DeJean-Hughes and Abby Wick and myself on it. And you can kind of see the scale of these tillage trials. This was actually on that field, that's Fargo Silty clay soil that the moisture and temperature grass just came off of. We have these big strips down the field with different tillage practices. We had chisel plow in the fall with a spring field cultivator pass. We had 2 different types of strip tillage, a fall shank system. We also had a spring culture system where fertilizer was put down in the berms with the strip till implements. We also had a shallow vertical till that was only tilling down an inch or 2. It was more so just for chopping up the residue and thinning down the residue layer. It's not really doing any tillage or digging itself. It's just for thinning down that residue layer to try to see if we could get a high % residue cover, which is good for erosion control, but also being able to thin down that residue layer to get water to evaporate out in these soils that can be difficult on getting water to drain down. And here in the foreground in the image, this was done on one half of the field that was tile drained. In the background of the image, you'll see the exact same setup and strips back there. That's on an untile drained portion of the field as well. But this gives you an idea of scale, and you can see the planter out here in the spring planting. So temperature-wise, with soil warming up is about what you would expect in between these different types of practices. We also had areas that were in no-till that we monitored, that we had as buffer strips around these research tiles that we ran for 4 years on a variety of sites. So these are average soil temperatures across the 3 farms for it. The 3 farms that we had, the one that was on the Fargo Silty clay soil, high clay content. We also had another one over by Barney, North Dakota, that was on a sandy loam site. And then the 3rd site over near Fergus Falls, Minnesota, that was on a loam, clay loam site. So we covered a lot, clay soils, loamy soils, and sandy soils for it. So these are average temperatures across all 3 farms, and they fall almost spot on with that Fergus Falls site that had the loam soils for it. But what you see is that, the chisel plow soil or chisel plow treatments and the berms of the strip tills, whether it was fall shank or spring coulter, it did not matter. Those systems warmed up just pretty much the same. And many times the strip till was just slightly ahead of that of the chisel plow. Now, if you look at the no-till areas, they were typically 7, 8, 9 degrees cooler than that of the chisel plow areas and the strip till berms, as you would expect, because there was a lot of residue and thick residue, and these were in corn soybean rotations. The vertical till, to where we have around 70–80% residue cover on it, but not doing much digging, it's just thinning down that residue layer. They warmed up only a few degrees behind the chisel plow and the strip till berms on it. If you look at where the no-till temperatures were and the chisel plow or strip till temperatures were, the vertical till didn't even fall necessarily midway. It's still leaning towards that the chisel plow and the strip till, because we thinned down the residue layer, able to get water out, and it was able to warm up quite nicely in there, even though it has a very high amount of residue cover on it. And on our vertical tills, we did 2-pass system, one in the fall and then one in the spring, where we also broadcasted fertilizer in front of it and used it to mix in, try to get a little bit soil contact with the fertilizer on that second spring pass. And if you think about drying down wise, match the same, pretty much the same story here. Story here, the chisel plow and the strip till berms dried down the most, as you would expect. The no-till had higher water content, as you would expect from abundance of residue there. And that vertical till, again, it dried out. If you look at where the no-till is versus the chisel plow and the strip till on it, it dry out midway. It still leaned towards being closer dryness-wise to the chisel plow and the berm of the strip till. Now, the nice thing on the strip till is that just a few inches away underneath the big layer or thick layer of residue that gets moved off right in front of the shank or the coulter, that the trash cleaners just move off to the side, you have an abundance of water right there. That's a nice storage that conserves and stays throughout much later into the growing season, and when the plant needs water and late summer dry spells perhaps, but it's of no consequence to the early year temperatures in the berms there. So that's a nice combination of getting best of both worlds of drying, warming, but yet also conserving water for times when the crop will need it the most for it. Now, what does that all mean by the end of the year, yield-wise? Well, let's take a look at some of this real quick. Try to go through this gracefully to some extent. So here we're looking at the Fergus Falls and the Barney site. So this is the Fergus Falls site, is the one with the loam, clay loam soils. The Barney site is the one with the sandy loam soils. This was corn yields for 2015. Here we saw one treatment was different from the rest at the clay loam site. The strip till with the shank that was done in the fall yielded about 7 bushels, 6-7 bushels lower than that of the other treatment systems, which didn't, none of those differed at all from each other. And the thing is that that strip till with shank wasn't because of the strip till system itself. What happened here was when we were putting in the fall chisel plowing, vertical till pass, and that strip till with shank pass, the chisel plow was put in, the vertical till was put in, but when we started putting in the strip till with shank, it started raining at the site. So we held off, we waited a little while, but then the ground started freezing. Or we started getting into where the ground was going to start freezing. So, and we didn't want to kind of chunk in the strip till after the ground had frozen, because we'd actually have to come back and refresh the strip in the spring anyways, probably because it'd be too chunky. So we went ahead and put in the strip till with shank when it was probably a little bit too wet. And when we dug down and looked at the sidewalls, you could see that it was kind of glossy, which indicates that it had a smeared sidewall to it. A good indicator, or what you really want to look for, whether it's the bottom of a tillage depth or on sidewalls of something like strip till, is that if the soil looks like it's a matte finish, that's good. You didn't smear anything. But if it looks like glossy paint on it, then you smeared the soil, and that has a yield consequence to it. And in this case, tilling when it was too wet had a 7 bushel per acre consequence to it, not because of the system, but because of timing, the soil moisture condition when it went in. And the thing here that I want to really emphasize is that tilling to dry a wet soil kind of goes against our intuition on what actually happens. If it is, as a rule of thumb, if it is too wet to plant, it is too wet to till without smearing that soil. And so if you're going to till a soil to get it to dry out so that you can plant, the tillage itself is going to cause a yield reduction there. So very cautious in the spring on wet soils to try to use tillage to increase the amount of evaporation that's going to occur for it. What I would suggest is actually just try to either Don't do any tillage at all, and really get to know your planter much better, because our planters are pretty awesome out there. You can adjust them and get used to. This might be your opportunity to see what your planter can really do in a high residue situation, or go in and just thin down the residue layer without actually digging and smearing that soil for it. So, but if we go on to 2016 in soybean at both those fields, no differences at all between any of the tillage treatments, even though there were differences in temperature and moisture early in the year. In 2017, no differences in corn yields in between the two sites among the tillage treatments. In 2018, we did see a increase in about a 3 to 4 bushel per acre boost in soybean in the strip till, both of them, whether it's fall shank or sprinkle, at sandy site, because later in the year we had some dry spell in the summer, and that reservoir just a few inches off to the side apparently helped out that crop and gave it a nice yield boost at that point for it. So in general, soybeans are pretty resistant or intolerant to all sorts of things. They're a very tough crop, actually, except for salts. They're very weak on salts, but otherwise, very rarely do we actually see a tillage effect on soybeans, even though they're being planted after corn for it. Now, if we go to that silty clay soil, that high clay soil, what I want to point out here is in 2016 in corn, there's, as I mentioned before, there was the north side of the field was tile drain. That's the first 2 column of yield. The second 2 column of yield, that's the non-tile drain parts. We also noticed that I include saline and non-saline portions of the field, because the western side was a saline seep, the eastern side had no salinity problems on it. So we kind of have the combination of saline, non-saline, tile drain, non-tile drain to be able to take a look at. But in here in 2016 on the corn yields, the top table here, there was one effect of tillage, and that was the vertical till yielded around 20 bushels per acre lower in a lot of cases than all the rest. But again, this was not a tillage issue here. What happened here is that the fall pass went in, but then the spring pass, where we were going to incorporate or broadcast nitrogen fertilizer out in front of the tillage implement, and then use the tillage implement to incorporate it a little bit. Our equipment rep was actually out of the country, and we weren't able to do the second pass. So fertilizer got broadcast on the surface, and we just got a lot of emission losses of nitrogen there. And so this is a nutrient management issue. This is not a tillage issue or tillage effect here. It is a fertilizer effect for it. So, you know, the biggest part about getting these tillage programs to work is getting down the nutrient programs first for them. Typically, nutrient consequences to yields are much higher than that of a yield consequence or a yield benefit from tillage either. So, and in most cases, if you've got the fertilizer program figured out and down solid, your tillage effect tends to disappear, good or bad wise on it. So, nutrient availability and access is a good way of kind of eliminating even the need for tillage whatsoever in a lot of systems. In the bottom graph on soybeans here, what we saw was that there was no tillage effect on it, but we actually saw what appeared to be a difference in whether the ground was tile drained. The blue circle here is the 2 tile drain areas, whether it was saline or non-saline, and the red circle is the untile drain area. And you can see that there's around a 7.5 bushel difference in between a boost from tile drainage versus area that wasn't tile drained for it. And this is something that I really want to emphasize here, is that Here, the drainage was controlling the issues for it. And when I talked about when you have two options of getting rid of water, drain it down or evaporate it up, draining down is a much more efficient and productive way of getting the soil to dry out in terms of crop success and yields for it. And there's a difference in between having a drainage problem versus having a tillage or residue problem with excess moisture. A tillage program will not be able to fix a drainage problem. So if you have a drainage problem, it's going to take a drainage solution to deal with it, because tillage is not going to be in the same ballpark of just being a viable tool to fix a drainage issue. You won't be able to do it with it. So being able to identify what's a drainage issue versus which is much more severe issues versus what's a residue moisture excess issue is important on picking what's even your right approach to dealing with your specific fields and situation. So this next graph here, you know, that was, or the previous graphs, that was for those research trials that we had on 3 farms of production scale. One of the things that Jody Dijon-Hughes and I did in our Upper Midwest Tillage Guide that was published in 2017 that you can Google and check out, a lot of great information in there. We looked at a variety of research trials in the regions and summarized those on when, how often, what's the odds of having a corn yield response to different tillage methods out there. And so this chart right here shows 18 site years across North Dakota and Minnesota in between 2005 and 2012. And what we have here is that 44% of the time in a corn system, corn soybean system, it didn't matter what you did tillage-wise, they yield the same. 44% of the time, strip tillage will outperform the other tillage options for it, and only 12% of the time will chisel plow actually give you a yield boost compared to something else that's significant. And so if you think about 12% of your fields, you know, it's like 1 out of every 8 fields, or 1 out of every 8 years, you can get a chisel plow to get a yield benefit for it. So if you think about the economics of it and your tillage, if you're doing tillage, there's some cost associated with that tillage pass or those 2 tillage passes for it. You want to be able to just not only break even, you need to make more yields to make it worth the time to profit off of that. So if you're only getting a 1 out of every 8 fields, 1 out of every 8 years return on seeing a yield boost, that yield boost has to be enough to account for all those years and fields that aren't responding to it. And the vast majority of the time, we just don't see chisel plowing being able to pay for itself. Usually it's a loss because of these odds and occurrences of when it actually sees a yield boost, and that yield boost isn't high enough to cover those other years in other fields. If we go to soybeans, again, soybeans are very resilient, and actually my number disappeared here. This green, this big green area, about 74% of, or 76% of the whole graph is they don't react to different tillages methods out there. They just, you know, they yield the same for it. 18% of the time, you might see a yield boost from strip till because of the water being available if it gets dry periods of the year. And then chisel plowing with field cultivation, only 6% of the time you see a benefit or a notable yield boost from it. So 1 out of every 15 years, 1 out of every 15 fields, that yield boost has to be able to also pay for to not only break even, but try to make some money off of it as well for it. And this is for 17 site years in that same interval from 2005 to 2012 on a variety of studies in between North Dakota and Minnesota. In this next graph right here, Well, this next section we go into, so this would be still waiting to harvest out in your fields. The crop's still in there from 2019. So here, the first thing is when you go into harvest, if you can, avoid those ruts, because ruts will have a consequence for the next couple of years to come up on. So wait for the soils to dry as much as possible before you get in. So you don't have to spend more time out in the field leveling and filling, and then also having the consequences for the next couple of years from the compaction that would have occurred underneath those ruts. If you have ruts, compaction happens. If you're able to harvest if you were able to harvest when it was frozen out in the field, look to minimize your tillage. Again, if the soil is too wet to plant, it's too wet to till without smearing it and have a yield consequence because of that smearing. This is a great opportunity actually to get to know your planters better than ever if you haven't already. Planters are really awesome out there. You can deal with very high residue zones and get some really great yield stands and a great crop from a field if you set up your planters well and adjust them often. Ideally, for every field that you're going into, even as painstaking as that may sound, but adjusting the row cleaners, making sure the bars are level, adjusting the row down pressures, certainly taking a look and adjusting that closing wheel, making sure that it's getting, it's closing right, but then it's also not pressing down too hard where you're getting some lift and the variable seed depth on it, and making sure that those disc openers aren't dull for it. Going through and doing those small adjustments will make a world of difference for getting a good stand in high residue conditions for it. So. And some areas, it's going to have to probably consider preventative plan based on the timing that crops come out and depending on what our weather or spring rainfalls end up doing out here. So depending on when that's done in the spring rains, you might look into cover crop options if you're going into PP grounds. Also check out the timelines and rules, see if that November date is changing and what you might be able to do with something that you may plant cover crop wise out there, whether you graze it or harvest it for a cover crop seed itself or something. So check out the rules on prevented crop. And also note that not only were we wet up here, but pretty much the whole entire Midwest was tremendously wet. So some seeds might be in higher demand throughout the entire Midwestern region and may affect seed availability for some of those cover crops. And then that last category there, harvested during the fall or winter, but look at those ruts that came out from it. And again, everyone had to face some tough decisions. No one likes to let a crop over winter, but some fields were pretty severely rutted this year. So what can you expect from that? One of the things I like to do is kind of visualize what happens underneath the ground. This is a cool image from a field day from a number of years ago to where they dug out these pits, lined the soil back, but then put in lighter colored sand, drove heavy equipment over it. So there's a manure hauler here, tires, that's two different types of tires, but the biggest thing is that the one on the right is overinflated, that's inflated at the road conditions. The one on the left is inflated for field conditions. If your tires are inflated for the road, so they're 40 plus PSI, they're too high for in the field. You want to get those down around 10 PSI if you can to be able to get all the area, full area of the tread on the ground to distribute the weight. But here, just in between overinflated and underinflated, you see that the soil is still caused a rut, but how deep the compaction went with the bending of those. You can see visually the bending of those sand layers there. I highlight them in red. You can see that the overinflated one went much deeper than the properly inflated higher for it. Even though the rut depth, where this yellow line is here, is the same. That's what I want to emphasize here, is that the depth of the rut, unfortunately, doesn't tell you much about how deep the compaction went. The only thing you know for sure is that you do have compaction underneath it and out to the sides from that rut. And with our equipment weights and axle loads that we have these days on combines and grain wagons and stuff like that, our compaction is deep, and it goes deeper than what tillage implements can reach for certain. And so what can you expect with these? Well, back one of the last times we had some really wet conditions in 2009, Jody John Hughes had 7 farms in western Minnesota where it looked at fields that had ruts in them, and then adjacent areas within those fields that didn't have ruts in them that the producers stayed off of. And they looked to see what consequence that had on the next year and the year afterwards, corn and soybean yields from them. And on those rutted areas, they filled in the ruts with a chisel plow before they went in and planted on them. So, and you can see on the left-hand figure here, this is the first year after the ruts in corn, and you get these nice, the left image is where there were no ruts. So nice even cob size and grain counts on them. On the one on the right is where the ruts were, and you can see the variability in how the plants were doing with it. So that has a yield consequence. So in 2010, all 7 locations were in corn, in between rutted and non-rutted area. The stands didn't differ, the grain moisture didn't differ. There was significantly lower plant heights in the rutted areas, and also the growth stage lagged behind, as you would expect. And there was a 17% hit or drop on the yields from those rutted areas in that first year after the ruts occurred in. In the second year afterwards, when these fields were in soybeans, the exact same story. Stands and grain moistures didn't differ. Plant heights were lower in the rutted areas. Growth stage lagged behind in the rutted areas. And again, a 16% loss on yields in those areas for them. They didn't go into a third year afterwards, but this data is very consistent with the much broader literature across the world for a variety of crops. If you look at deep compaction that goes beyond the topsoil, beyond the reach of tillage equipment and stuff, you'll see a yield drop around 15 or 20%. Sometimes it might extend up to 30%, sometimes it might only be 10%. But in that range, in the first couple of years, you'll see a multiple year effect from that then will taper off and then eventually get back up higher. There may be even a permanent yield consequence that doesn't emerge every single year. When you think 5, 6, 7, 8, 9, 10 years afterwards, but on inclement weather years, you might see a 5% drop, a 2 to 5% drop on those yields because of that deep compaction that just takes a tremendous amount of time to heal. So some strategies for dealing with ruts, if you have those, is just level off the ruts and only till only as deep or shallower than the rut itself. Just enough to be able to get in and spring plant. It's probably going to take a couple passes to do it. Thing is that subsoils dry slower than topsoil, so the only way to insult compaction is to smear it. So if you're digging into wet subsoil by trying to go deeper than the bottom of the rut, you're probably not doing much any good, and you potentially could be actually making it worse, because the only way to insult compaction is to smear the soil along with compaction. You get these slabs of soil that's really unpleasant to plant into. For ruts that are less than 4 inches, you might use a secondary tillage implement to do it in a couple passes. If it's greater than 4 inches, then you might get out the chisel plow and start filling those in. And again, multiple passes would probably be needed for it. Good strategies for any year is probably adjusting the tire pressures for them. finding ways to minimize the number of passes on your fields, because with a typical corn soybean rotation that has tillage in the program, you can easily cover 70, 80, 90+% of that field within a given year. So minimizing the number of field passes will minimize the odds of compaction that you have to deal with. Minimize your loads, control traffic if you can, based on the size of equipment that you had, and avoid wet soils if possible. Avoid those ruts, because you might get a crop out, but then you can expect that 15 to 20% yield loss for the next 2 years because of it, especially on fields that have from one end to the next. Every single pass of the combine, there's a rut, which we've had a number of fields like that this year because of the tough, wet fall that we endured. And the biggest thing is patience. A few extra days of waiting will go a long ways of helping protect your soil from the occurrence of compaction occurring in the first place. Which, if you can prevent the occurrence of it, then you don't have to worry about the time needed to try to remediate it and the yield losses that are going to come with it, even when you try to remediate it. And a few items here is that that I like to throw out there is that mechanically working the soil homogenizes it. So this is a strategy for any year still. As a soil physicist, I think of what makes a good soil, good healthy soil. A lot of folks think biology-wise in a physics manner. I think about what a great soil is. A soil that can drain very efficiently and well, which you have to have pores, mini pores, big pores to be able to do that, but it's also strong and firm enough to hold up your equipment. That is what makes a good healthy soil, is having simultaneously good drainage and strong soil to hold you up on. When we mechanically work a soil, we homogenize it, we make it weaker to where equipment doesn't stand on top of it, and it actually can reduce drainage for it, because we're aiming for water going up, not water going down necessarily, particularly below that tillage depth for it. And it's a high input on your behalf. Natural ways, not mechanical ways, but natural ways that soils aggregate. They add a lot of cohesion and friction to the soil, so that's what makes them strong, is when you have cohesion and friction in the soil in between those aggregates. They can stand up, and because you're making aggregates, the spaces in between them is what lets water drain very well. Unfortunately, we do not have a mechanical tillage implement that works at the aggregate scale, at those aggregate sizes. Our equipment works at inches to a half a foot or a foot scale, which is too big to be able to work and get both those realities of good drainage and strong, firm soils for equipment to stand on to happen, to actually occur. So unfortunately, we just don't have that technology that exists, but we have many natural ways that does exist. Every time you get in another crop in a root system that's not broken up afterwards, every freeze thaw, wetting and drying with cracking and shrinking and swelling that occurs, you get aggregate formations. And tillage innately homogenizes and unworks aggregation for it. So something to keep in mind, because these wet falls are probably, well, one, they happen and they re-happen. And so if we're dealing with compacted soils from ruts and trying to fix those, that has a multi-year consequence to it. If we have wet events every 10 or less years, then the number of years that we're maximizing our yields become quite limited on it. So, and that's what I've got for you for challenges and some thoughts and hopefully advice for you for dealing with residue, high residue after a wet harvest, some expectations from different tillage programs that you can have, and consequences of tilling when it's too wet. Certainly a thing to exercise caution with this spring, and then also dealing with ruts for quite a number of folks that have having to deal with those this spring, or did have to deal with them also in the fall. So I have my email address here. Feel free to contact me if you ever have any questions or want some more information on these studies. And I've put a few links out here, one for that Upper Midwest Tillage Guide that I mentioned earlier that Jody and I wrote back in 2017. Also have an op-ed that I had in Ag Week back in the fall on this idea, on this content right here, as well as a few other interesting or amusing links that you might find useful. So I appreciate the opportunity to speak at this virtual Langdon Soil Health Workshop, and I hope you all are doing well and staying safe out there. And again, please feel free to contact me at any time if you wish. Thanks again, and take care. Bye-bye.